Okay, we should be live. Test my microphone. I'm also losing my voice, so I have to stay close to the mic. Close to the mic. Okay, we'll use the video, the filter thing. If the camera is working, what the presets normally will go less FPS. Hey, we'll go for like 15 FPS. Edge threshold, let's make it 50 or so. Okay, that seemed to work okay. So I have 15 FPS. Pop it in another window. Pop it in another window. Okay, that should be fine. Should be fine. So working this website, as you know. Hey, go check it out. We'll be making more applications. So this one is a TMS simulator, transcranial magnetic simulation. We're meant to have a model of the brain, but something is up and it's missing. We're missing a model of the brain. We actually have a model of the brain somewhere locally, but I thought the bot could actually try to bring it from GitHub. It's trying to bring it from GitHub. Okay, so doing TMS, I'll just do how professional podcasters can do an overview of what it is. Just download that just in case. The reason I'm downloading is because, well, yeah, don't worry about it.
Welcome to the deep dive.
Hello.
Okay,
Hello.
so today we're plunging into a topic from your source material that honestly feels a bit like science fiction.
Right.
Transcranial magnetic stimulation, TMS.
Yeah, it sounds complex, but it's essentially a non-invasive way to interact directly with the brain using magnetic fields.
Right, magnetic fields. So our mission, like always, is to unpack the sources you've given us, really get into how TMS works, what it's used for, and maybe why it's seen as such a big step forward for treating some really tough brain conditions.
Exactly. Let's get into it.
Let's figure out how this magnetic magic actually happens.
Okay, so it's this interesting mix, really old physics principles, but very modern neuroscience application. At its core, TMS, it's a procedure using magnetic fields.
Okay.
And these fields influence nerve cells in the brain.
Right.
Crucially, without any surgery or anything invasive.
Okay, non-invasive, that seems key. And your source material really stresses its growing use, right, for neurological stuff, psychiatric conditions, especially depression.
Yes, depression is definitely a major focus. It's often presented as a real alternative, particularly for patients who, haven't responded well to other treatments.
Like medication or therapy.
Exactly.
Yeah.
Or maybe those aren't suitable options for them. For some people, TMS can be a really important pathway forward.
Okay, so let's get into the how. Walk us through the mechanism. How can a magnetic field outside the head actually affect brain cells inside? What's the physics?
Right. Well, it actually goes back quite a way. 19th century, Michael Faraday.
Faraday. Wait, the electromagnetic induction guy.
That's the one. Electromagnetic induction, that's the absolute foundation here.
Okay, so changing magnetic fields create electrical currents. How does that apply?
So the TMS device has this specialized coil. An electrical current runs through it, and this generates brief but pretty powerful magnetic pulses.
Okay, powerful magnetic pulses coming from this coil,
And that coil is placed right against a specific spot on the patient's scalp.
right on the head.
Yep. And here's the kind of amazing part, that magnetic field. It just passes straight through the skull, harmlessly.
Wow, okay. No need to cut anything, it just goes through the bone.
It does. But then, once that magnetic field gets inside the brain tissue, because it's changing rapidly, remember?
Faraday's principle kicks in?
Faraday's principle kicks in.
Right.
Exactly. It induces or creates a small electrical current right there in the brain tissue itself.
So the magnet outside makes electricity inside.
That's the connection. And this induced current, even though it's small, it's focused, and it's just strong enough to influence the neurons there,
The brain cells.
the brain's main signaling cells, yeah.
How does it influence them? Just gives them a little jolt.
It causes them to depolarize. Basically, it changes the electrical charge across the neuron's membrane for a moment.
Okay, depolarization. And if that reaches a certain point,
If it reaches the threshold, yep, they fire. They send off an electrical signal. It's called an action potential.
which is how neurons talk to each other.
That's the fundamental communication. So by carefully controlling these magnetic pulses where they go, how strong they are, TMS can essentially make specific groups of neurons fire, or it can influence their pattern of firing.
Right, so by making them fire, or maybe even stopping them from firing too much in a very specific spot,
Yeah.
you're sort of fine-tuning that brain circuit.
That's the goal, yes. If a circuit is, say, underactive in depression or maybe overactive in anxiety, you're trying to modulate that activity, nudge it back towards a more normal pattern.
Rebalancing.
Rebalance, exactly.
Now, your sources mentioned it's not just about one pulse, right? The pattern of pulses is really important. This is where repetitive TMS comes in, RTMS.
Absolutely. A single pulse has a fleeting effect.
Yeah.
For therapy, you need repetition. And the way you repeat the pulse is the frequency, the pattern that determines the effect.
Okay, so tell me about these different patterns. What if you pulse fast? Like, say, 5 times a second, maybe more.
Okay, so that's generally called high-frequency RTMS, usually 5 hertz, so 5 pulses per second or higher. And this typically has an excitatory effect.
Excites the neurons, makes them more active.
Exactly. It tends to increase the activity in the brain region right under the coil. So it's used when you think an area is underactive.
Like in depression, your source mentioned a specific area.
Yes, the classic example is stimulating the dorsolateral prefrontal cortex in depression. That area often shows reduced activity in people with depression, so the idea is to boost it.
Okay, high frequency ramps things up. Makes sense. What about the opposite? Slow pulses, maybe just once a second or even less.
Right, that's low-frequency RTMS, usually 1 hertz or lower. And this generally has the opposite effect. It's inhibitory.
So it quiets things down?
It tends to decrease the activity in the targeted region. So you'd use this for conditions where you think a particular brain area might be overactive.
Okay, examples.
Your sources mention things like some anxiety disorders or potentially trying to reduce the activity in areas linked to auditory hallucinations and schizophrenia.
Gotcha. So you've got this toolkit, boost or inhibit, high or low frequency. But these effects from one session, they don't last forever, right? How does doing this over, say, several weeks actually lead to lasting change?
Ah, that's a million-dollar question. And the answer seems to lie in one of the coolest concepts in neuroscience, neuroplasticity.
The brain changing itself. I love this topic.
Me too. It's fundamental. The brain isn't static, right? It's constantly adapting, rewiring, changing its connections based on experience.
Forming new pathways, strengthening old ones.
Exactly. And the idea is that repetitive TMS stimulation actually taps into and guides this natural plasticity.
How? How does zapping it basically encourage it to rewire?
Well, the thinking is that repeatedly making those neurons fire together or inhibiting them together strengthens or weakens the connections, the synapses between them.
The junctions where they communicate.
Precisely. And over the course of treatment, these repeated changes in synaptic strength seem to lead to more stable, long-lasting alterations in how that whole brain circuit functions.
Okay, are there like biological terms for these changes?
Yes, there are. High-frequency stimulation, the excitatory kind, is thought to promote something called long-term potentiation, or LTP.
LTP sounds important.
It is. Think of it as making the connection between two neurons stronger and more efficient when they fire together repeatedly. Neurons that fire together wire together, essentially.
Oh, okay, so you're strengthening a pathway. making it easier to use.
You got it. And conversely, the low-frequency stimulation, the inhibitory kind, can induce long-term depression, or LTD.
Depression, like the mood disorder.
No, different meaning here. LTD in this context means a weakening of the synaptic connection. It makes communication across that synapse less likely or less efficient.
Got it. LTP strengthens, LTD weakens,
Yeah.
and both are part of how the brain learns and adapts normally.
Exactly. They're fundamental mechanisms of plasticity. So TMS seems to be leveraging these natural processes.
So it's not just a temporary zap, it's more like training wheels for the brain circuit, guiding it to rewire itself in a more helpful way.
That's a really good analogy, actually. You're using the stimulation to guide the brain's own capacity for change towards a therapeutic goal.
Okay, this sounds incredibly targeted, but how on earth do they know exactly where to put the coil on someone's head and how strong the pulse should be? People's heads and brains aren't identical, right?
No, they're not. And that's a really crucial point. There's a calibration step, a personalization step that happens before treatment starts. It's called motor threshold mapping.
Motor threshold mapping. Okay, break that down.
So first, they position the TMS coil over the part of the brain that controls movement, the motor cortex.
Okay, the bit that makes your hand move, for example.
Exactly. Then they deliver single TMS pulses and start increasing the intensity, the power of the pulse, bit by bit.
And they're watching the patient.
They're watching, usually the patient's hand or thumb.
Yeah.
They keep increasing the intensity until they see a small, consistent twitch or movement in the hand.
So the twitch tells them, okay, this intensity is enough to make neurons fire in this specific person's brain.
Precisely. The minimum intensity needed to get that visible muscle twitch about half the time. That's the individual's motor threshold.
A personal dose.
Exactly. It serves as a reference point. They then use a percentage of that threshold, say 110% or 120%, as the intensity for the actual treatment pulses delivered to the target area, like the prefrontal cortex.
And how do they find that prefrontal target spot?
Usually it's located based on standard measurements from the motor hotspot they just found. Sometimes they might use brain imaging, like an MRI, to guide the placement even more precisely.
That's pretty cool, using a muscle twitch to calibrate a brain treatment. Now, your source material also mentioned a couple of newer variations on TMS.
Yes, the technology is still evolving. People are exploring ways to reach different areas or just make treatment more efficient. One variation is deep TMS, or TTMS.
Deep TMS. Sounds like it goes deeper.
That's the idea. It uses a different kind of coil, often called an H-coil because of its shape. This design allows the magnetic field to penetrate further into the brain tissue
Okay, reaching deeper structures.
and stimulating a larger volume of brain tissue compared to the standard figure-8 coils used in regular RTMS.
So that would be useful if the brain circuits involved in a condition are, well, deeper down, not right on the surface.
Exactly. Your sources mention its use for things like obsessive-compulsive disorder, OCD, where some of the involved brain networks are thought to be located deeper within the brain.
Makes sense. And there was another one. It sounded really fast.
Yes. Theta burst stimulation, or TBS.
Theta burst.
This is a newer form of RTMS. It delivers the pulses in these very short, rapid bursts in a pattern that actually mimics the brain's natural theta brainwave rhythm.
Okay, mimicking natural brain activity. What's the big advantage there?
Speed, efficiency. A full session of TBS can be incredibly short.
How short?
Sometimes just a few minutes, like 3 minutes, compared to maybe 20, 30, even 40 minutes for a standard RTMS session.
Wow, 3 minutes versus half an hour or more.
Yeah. And studies suggest it could be just as effective, particularly for depression.
That's a game changer. Cutting down treatment time that much has got to make it way more accessible for people.
Absolutely. It addresses a major practical barrier fitting those daily sessions into life.
Okay, so let's try and bring this all together. What we've unpacked from your source material today is that this TMS, transcranial magnetic stimulation, it's a genuinely innovative, non-invasive approach.
Right. It used that basic physics principle, electromagnetic conduction, from Faraday.
To send magnetic pulses safely through the skull. No cutting involved.
And those pulses then create these little targeted electrical currents inside the brain.
Which can then excite or inhibit nerve cells, depending on the pulse pattern, the frequency?
Exactly. High frequency tends to excite, low frequency tends to inhibit. And doing this repetitively, day after day.
That's where the magic happens, right? It taps into the brain's own ability to change itself. Neuroplasticity.
Right. It guides plasticity through things like LTP strengthening connections and LTD weakening them, leading to potentially lasting changes in brain function,
And it's personalized using that motor threshold mapping to get the dose right.
which makes it a really targeted therapy, offering new hope for people with a growing number of these challenging neurological and psychiatric disorders.
Yeah. Understanding this whole process, from Faraday's idea through to neuroplasticity, it really gives you a much deeper insight into where modern brain therapies are heading.
It really underscores how dynamic the brain is. It's not just a fixed computer.
Definitely not. And it's fascinating that TMS seems to work because the brain is dynamic. It relies on that capacity for change, neuroplasticity.
That's the key mechanism, it seems.
So here's something to think about, maybe for you listening. If the effectiveness of TMS really hinges on stimulating and guiding the brain's own ability to reorganize, what other kinds of therapies might become possible? What other frontiers could we unlock by finding new ways to precisely guide the brain's inherent capacity for change?
Hmm. That's a big, exciting question for the future.
Okay, so I obviously having a few issues. Let's actually bring a prompt engineer. Let's bring in a prompt engineer. Okay, can you overview what do you see on the screen real quick?
I see a TMS simulator with settings for stimulation intensity and pulse frequency. There are also two coil type options, figure 8 and circular, and a button to start the simulation.
Okay, and this code, can you overview the code real quick?
The code appears to be using React and 3.js to create an interactive TMS simulation. It includes components for handling stimulation settings, displaying the coils, and managing the 3D scene. There are also functions for loading the brain model and handling interactions.
Okay, do you see what the error is?
Yes, I see an error message that says, error while loading the brain model, failed to fetch. This suggests that the application is having trouble loading the 3D brain model from the specified location.
Okay, do you think we should continue with React or just do vanilla HTML JavaScript?
Given the error with the 3D model loading, switching to vanilla HTML and JavaScript might simplify the process and make it easier to manage the model loading. It could help us focus on the core functionality without the complexities of a framework.
Okay, and what's the developer currently doing? What's the plan of attack is?
The developer is currently restructuring the code to use vanilla HTML and JavaScript instead of React. The plan is to create a standard HTML file, set up the basic 3D.js scene, and then load the brain model directly using JavaScript. This should simplify the code and address the model loading issue.
Again, we have the model available locally as well.
Yes, the plan includes loading the 3D brain model directly from the local file structure. The code is being modified to use relative paths to access the .obj files from the local directory, ensuring the model is loaded correctly.
Okay, so we're only loading a model of the brain from a from the server. How about the coils? I don't see the coils anymore. There's something wrong. Can you look at this? Well, yeah, so those models of the brain will be local, but then the coils should still be generated in the code.
You're right, the brain model is loaded locally, and the coils should still be generated in the code. If the coils are not visible, it's likely an issue with the 3D.js scene setup or the rendering logic that needs to be reviewed in the JavaScript code.
No, wait a sec. We need to ask the developer why the coils are not showing.
You're right, it's important to address the issue with the coils not being displayed. We should ask the developer to check the 3D.js scene setup and ensure that the coil models are being correctly created, added to the scene, and rendered. This should help resolve the problem with the coils not appearing.
Or will the coils not appear unless the brain model is loaded?
It's possible that the coils are designed to appear only when the brain model is loaded, as they might be positioned or related to the model structure. If the brain model fails to load, it could prevent the coils from being displayed as well. The code logic would need to be checked to confirm this dependency.
You have to bear with me. I'm looking for the object.
Oh.
Yes, so the brain object. Can you explain how that would work?
The brain object in the simulation is likely a 3D model loaded from a file, such as an OBJ file. This model represents the structure of the brain and is used to provide a visual reference for placing the coils. The simulation uses 3D.js to render this model in the 3D space, allowing you to visualize the brain and the coils in relation to each other. The brain model serves as a guide for positioning the coils accurately within the simulation.
Okay, so it needs to be the object, the brain model needs to be in a static folder, is it?
Yes, that's correct. For the simulation to load the brain model correctly, the OBJ file for the brain model needs to be placed in the static folder of the project. This ensures that the simulation can access and load the model properly. The developer should make sure the file path in the code correctly points to the location within the static folder.
Okay, so we have this as a project structure.
Got it. Understanding the project structure is crucial. The developer should ensure that the OBJ file for the brain model is placed in the designated static folder within the project directory. This will allow the 3D.js loader to correctly locate and load the model. If the file is in the wrong place, it can lead to errors and the model won't be displayed.
Oh, actually, we do have the coils loading. Okay, so we're only missing the brain model.
Ah, I see. If the coils are loading correctly, but the brain model is missing, the issue is likely related to the brain model's loading process. The developer should double-check the file path for the brain model in the code and ensure that the model itself is properly located and accessible within the static folder. Additionally, they should verify that the loading code for the brain model is correctly implemented and handling any potential errors.
Okay, let's unpack this. Imagine for a moment being able to um, visualize something invisible.
Yeah, like seeing exactly how a magnetic pulse from outside the skull.
Right, how it creates an electrical field inside the brain and, influences activity.
It sounds incredibly complex, maybe a bit sci-fi even.
It does. But that's exactly what we're diving into today. The world of transcranial magnetic stimulation simulation. TMS simulation.
It's this powerful computational approach. Takes all sorts of data about a person.
And let's researchers model that whole interaction digitally. We've gathered your source material, which lays out this really fascinating process step by step.
Yeah, it breaks it down quite nicely.
And our mission for this deep dive, using these insights, is really to get why simulating TMS is so important.
Right. It's about seeing that magnetic field interaction clearly.
Understanding the sort of underlying mechanisms.
Figuring out better treatment protocols.
And ultimately moving towards, truly personalized therapies. That's the goal here.
Exactly. And the way it's approached, according to the material, it's like building something complex piece by piece.
A multi-stage process.
Yeah, starting with creating a digital twin of the person's head. Well, it's absolutely foundational for everything else.
Okay, so let's jump right into that first stage then. Creating this realistic head model, this digital twin. Why is getting this detailed map so critical right at the start?
Well, what's key is that the electric field induced by TMS, and that's the bit that actually interacts with your neurons, right?
Right, the E field.
It depends highly on the exact geometry, the shape, and the electrical properties of all those different tissues in the head.
Ah, okay. So like the brain itself, the skull, scalp, the fluids.
Precisely. They all conduct electricity differently. They all have unique shapes in each person. So without an accurate map of that whole landscape, you just can't predict how the magnetic field translates into that crucial electrical field inside.
Okay, that makes sense. You need this incredibly detailed map. So how do you actually start building this digital twin in the simulation? Where does the raw data come from?
It starts with data acquisition, actually quite similar to clinical practice. The standard way uses high-resolution structural MRI scans.
MRI, okay.
Specifically T1-weighted images, and often T2-weighted ones, too. These are really the gold standard for capturing that intricate anatomical detail you need.
So the MRI gives you the picture, like the raw anatomy. But the simulation needs to know what kind of material each bit of that picture is.
Right. How do you go from just an image to knowing this is skull, this is brain?
That's the next really crucial step. Image segmentation. The MRI scans get processed to differentiate between all those various tissue types.
Okay.
So things like the scalp, the bone of the skull, the cerebrospinal fluid, the CSF that cushions the brain, gray matter where lots of computation happens, and white matter, which is more like the brain's wiring.
All identified separately. Exactly. Each gets identified. And this is vital because, like we said, each one has its own unique electrical conductivity value. The sources stress that the accuracy of this segmentation is absolutely critical for the simulation to be realistic.
I can see why. If you get the conductivity wrong, the E-field calculation will be off.
Totally. Garbage in, garbage out, basically.
Okay, so you've got the high-res scan, you've segmented it into different tissue types with their properties. What's the next technical step to turn that into something the computer can actually, run physics simulations on?
Right. Then you move to mesh generation. You create a 3D volumetric mesh from those segmented images.
A mesh, like a net?
Sort of, yeah. A common technique for this is the finite element method, or FEM.
FEM, okay. Heard of that.
Think of FEM as taking a really complex, irregular shape like the human head and dividing it up into thousands, maybe even millions, of smaller, simpler geometric elements.
Like little building blocks.
Exactly. Often tiny pyramid-like shapes called tetrahedra. The computer can then solve the complex physical equations, like Maxwell's equations we'll get to, across all these many simple elements. It approximates the solution for the whole complex structure that way.
Okay, so breaking down the complex geometry into bite-sized computational pieces makes the physics calculations actually possible.
Precisely.
Are there specific software tools that researchers typically use for this whole anatomy-to-mesh process?
Yes, definitely. The sources highlight SimNibs quite a bit.
SimNibs?
Yeah, it's popular, it's open source, and it's designed to automate a lot of this, taking the MRI data, handling segmentation, handling meshing. It's considered pretty accessible.
That's helpful.
Another tool mentioned is SPM, statistical parametric mapping. It's well known for other brain imaging analyses, and its segmentation algorithms can sometimes be used as a preliminary step before maybe using other software for the meshing itself.
Okay, interesting. So there are dedicated tools to streamline this complex modeling stage.
Yeah.
Fantastic. So stage one is complete. We've built this incredibly detailed digital twin of an individual's head, mapped out all the tissues, their electrical properties, broken it down into a mesh for computation. What comes next?
Okay, so now we need to introduce the source of the stimulation itself. Stage 2 is all about modeling the TMS coil and then, crucially, calculating the electric field it induces within that realistic head model we just built.
Right, because you mentioned earlier, it's not the magnetic fields from the coil that directly excites neurons.
Exactly. It's the electric field it induces. That's the key player at the neural level.
So what does the simulation need to know about the coil to model it accurately?
It needs a precise digital model of the specific coil being used. This includes details about its shape. Is it a figure-of-8 coil, which is common, or a simpler circular one?
Okay.
Its size, and even the specific pattern of its electrical windings, that all affects the magnetic field it generates.
Wow, that detail.
Yeah, but thankfully, most simulation software packages, like SimNibs again, often come with pre-built models for a lot of the standard commercial coils. So researchers don't always have to, build that part from scratch.
That saves some effort. And just like in a real TMS session, where you place the coil and how you angle it must be super important. How's that handled in the simulation?
Oh, absolutely critical. Coil positioning needs to be defined precisely in the simulation. You basically tell the software exactly where the coil is located and how it's oriented relative to that digital head model.
Mimicking the real setup.
Exactly, mimicking how you'd position it on a real person's scalp. And what's really neat, the sources mention, is that if clinicians use neuronavigation systems for placement accuracy in a real TMS session.
Like those GPS systems for the brain.
Kind of, yeah. The coordinates recorded by those systems can often be directly imported into the simulation software.
Oh, that's a great link. Connecting the simulation directly to the clinical procedure.
It really is. It helps ensure the simulation matches what was actually done.
Okay, so we have digital head, the digital coil, positioned just right. Now for the big physics calculation, right? Finding that crucial electric field inside the brain.
This is where the fundamental physics comes in. Using the detailed head model and the coil model, the software goes to work solving Maxwell's equations of electromagnetism.
Ah, the famous Maxwell's equations.
Yep, those are the foundational equations describing how electric and magnetic fields behave and interact. By solving them within the specific context of that head's geometry and all those different tissue conductivities.
The simulation computes the E-field distribution.
Precisely. The precise distribution of the induced electric field throughout the brain volume. And this, as the sources emphasize, is where it gets really interesting because that E-field isn't just some abstract calculation.
It's the direct cause.
It's the direct cause of a change in the resting membrane potential of the neurons. So this E-field value, its strength and direction at any point in the brain, that's the key quantity we're ultimately after in this stage. It's the direct link between the external magnetic pulse and the potential for neural activation.
That's fascinating, the direct link between the calculated physics and the potential biological effect at the neuron level. Highlights the need for precision, doesn't it?
Absolutely. Small errors in the head model or coil position can lead to significant differences in the calculated E-field.
Makes sense. What software tools are typically used for the specific E-field modeling part?
Well, SimNebEase comes up again as a primary tool here. It's known for calculating the E-field with high precision.
And it has visualization tools too, you said.
Yeah, powerful visualization tool. So you can actually see where the field is predicted to be strongest within the brain model, which is incredibly useful.
About it.
Another tool mentioned is Slicer TMS. It's also open source and apparently offers more real-time visualization capabilities.
Real time. So you could potentially, like, move the virtual coil and see the E-field change.
That's the idea, yeah. Which could be particularly useful for things like interactive treatment planning, trying out different spots virtually.
Very cool. Okay, so we've progressed quite a bit. We've built the digital head, modeled the coil, calculated the precise electric field it induces everywhere in that digital brain. But knowing the E-field intensity, the sources say that's only part of the story.
Exactly. It's a critical part, but it's the trigger, not the whole response.
So the next stage takes us deeper into the neuroscience, simulating the actual neural response.
Right. The big question now is, how do the neurons and the networks they form actually react to that calculated E-field? This is stage 3. And it's noted as perhaps the most complex and also the most rapidly evolving area in TMS simulation right now.
I can imagine. Brains are complicated. How do researchers even begin to tackle simulating that neural response? Are they looking at single neurons or bigger networks?
They're doing both, actually. And these approaches give different kinds of insights. One approach is single neuron modeling.
Okay.
This uses really detailed, biophysically realistic models of individual neurons, sometimes called compartmental models.
Compartmental.
Yeah, they break the neuron down into different electrical compartments, soma, dendrites, axon. These models simulate how the calculated E-field at that neuron's location changes its membrane potential.
And whether it's enough to make it fire.
Exactly, whether it triggers an action potential. These models often incorporate very detailed neuron shapes, their morphology, and they're often based on principles like cable theory to understand how electrical signals travel along the neuron structure.
Wow, so you can simulate if one specific virtual neuron sitting in a particular spot with a certain E-field hitting it would actually activate.
Pretty much, yeah. It gives you that fine-grained view. But, as you know, the brain isn't just isolated neurons floating around.
It's all connected.
It's a massively interconnected network. So the other approach is network-level modeling. This shifts the focus to simulating interconnected groups of neurons or even larger-scale brain networks.
Okay, so zooming out a bit.
Right. These simulations explore the kind of broader impact of TMS. They ask questions like, how does stimulating one specific target area influence the activity of brain regions that are far away but connected through white matter tracts?
Ah, the downstream effect.
Exactly. Or how do different TMS protocols like the frequency or pattern of the pulses affect the overall network dynamics, or even processes like synaptic plasticity?
Plasticity.
Yeah.
The brain changing its connections.
Which is fundamental for things like learning, memory, and potentially therapeutic effects too.
Yeah, that sounds like a huge leap in complexity, simulating network interactions and plasticity. What kind of software or toolboxes are used for these really intricate neural simulations?
Yeah, it is complex. For models specifically looking at how the E-field interacts with detailed single neurons, NemoTMS is mentioned. That's an open source MATLAB toolbox. And then for building and simulating more generalized custom models of neurons or neural networks, there are powerful, more general purpose simulation environments like Neuron and Genesis. These are really flexible tools used widely in computational neuroscience.
Right, so specialized tools for bridging the E-field to the neuron and more general platforms for broader network modeling.
Correct. It depends on the specific question the researchers are asking.
Okay, so we've gone from the digital anatomy to the physics of the coil and E-field, now into simulating how individual neurons and potentially whole networks might respond.
Mhm.
Is there a final stage? Does it try to connect all this simulation work back to something we can actually, see or measure in a person?
Yes, absolutely. That's stage 4, and the source material describes it as the final frontier, essentially, predicting physiological and cognitive
The
outcomes.
final frontier. Okay.
This is all about bridging those simulated changes in neural activity, the firing patterns, the network dynamics to observable results.
Like what, for example?
Well, relatively simple things like a muscle twitch evoked from stimulating the motor cortex that's called a motor evoked potential, or MEP, or much more complex things like predicting an improvement in depressive symptoms after a course of TMS treatment.
Wow. Okay. Predicting symptom improvement from a simulation. That sounds incredibly challenging.
It absolutely is, and the source material is very clear about this, stating it remains a significant challenge.
Why is it so hard?
Well, think about the sheer complexity of brain function, how much variability there is between individuals even beyond anatomy, and just how intricate the link is between neural activity patterns and complex behaviors or subjective experiences like mood. It's a massive gap to bridge.
Yeah, no kidding. So even with that huge challenge, what kind of useful insights can simulations provide at this stage? How do researchers use them if predicting, say, depression scores is still out of reach?
That's a good question. Even though predicting complex behaviors perfectly is hard, the simulations still offer really crucial insights and, importantly, validation steps.
Validation. How so?
Well, for instance, researchers frequently correlate the strength and the location of the simulated E field in the motor cortex with experimentally measured MEPs, those muscle twitches we mentioned.
Oh, okay.
If their simulation predicts a strong E field in the hand area of the motor cortex, and they actually measure a large MEP in the corresponding hand muscle when they stimulate that spot in reality.
Then it gives them confidence that the model is doing something right.
Exactly. It helps validate and refine the head model, the coil model, the E field calculation. It's a way to ground the simulation in something directly measurable, even if it's a relatively simple physiological response.
That makes a lot of sense. Use something you can measure reliably, like an MEP, to check the accuracy of the earlier stages of your simulation before trying to predict something harder.
Precisely. It builds confidence in the underlying physics and anatomical modeling.
Are there other examples of how simulations connect to observable measures?
Yes, the material also brings up brain oscillations. TMS is known to be able to alter the brain's natural rhythmic electrical activity. Things like alpha waves, beta waves, gamma waves.
Right, the signals you see in an EEG.
Exactly. And these oscillations are linked to various cognitive functions. So, simulating how a specific TMS protocol might impact these oscillations is an active area of research. Often, this is done alongside real-world EEG recordings during TMS, something called TMS EEG co-registration.
So trying to match the simulated effect on brain rhythms with the actual measured changes in EEG signals.
It's another way to try and connect the simulation, the E field, and the predicted neural response to an observable physiological signal from the brain.
Okay, so putting all together now, we've really followed this fascinating journey. Started with building that detailed digital twin of the head, segmenting all the tissues, making the computational mesh,
And then modeling the TMS coil, solving Maxwell's equations to map out that crucial E field distribution.
then diving into the neural realm, simulating how individual neurons might fire, how networks might react.
And finally, trying to bridge that gap, however challenging, to predicting observable outcomes, validating with things like MEPs or comparing with EEG changes.
What's the big takeaway then from your sources about the overall value of this incredibly multifaceted simulation process?
The material really emphasizes that simulating TMS is this powerful integration. You've got medical imaging for the anatomy, you've got physics for the electromagnetics, and you've got computational neuroscience for the neural responses.
Bringing it all together.
Exactly. And by bringing these fields together through simulation, researchers are gaining, well, really unprecedented insights into exactly how TMS interacts with an individual's brain.
And the ultimate goal.
The ultimate goal, as highlighted again and again, is using these insights to pave the way for more effective and crucially more personalized treatments for a whole range of neurological and psychiatric conditions. It's about moving beyond a kind of one-size-fits-all approach.
Towards treatment truly tailored to an individual's specific brain anatomy and potentially physiology.
That's the vision, yeah.
It's pretty incredible, isn't it? How much complex computational work and deep scientific understanding goes into simulating something that, from the outside, might just look like placing a device on someone's head.
It really is.
This deep dive certainly reveals the incredibly detailed scientific process that's aiming to make this potentially powerful technique much more precise and hopefully more impactful for patients.
It truly does. It underscores the complexity, absolutely, but also the immense potential that simulation holds for guiding and optimizing these kinds of therapies in the future.
And that leads us perfectly into a final thought for you, our listeners, to maybe ponder. Given that significant challenge we discussed in stage 4, reliably predicting those complex, observable outcomes like actual symptom improvement, what might the next really big breakthrough in simulation need to look like? Perhaps it involves combining these physics-based neural models with other types of data, maybe genetic information, maybe detailed behavioral data. What will it take, do you think, to truly unlock the potential for fully personalizing brain therapies based on these sophisticated models? Something to think about.
All right. Picture this, a brain that looks like it's been tie-dyed with shades of purple and green. And then there's this big metal contraption that looks like two Siamese magnet rings having an existential crisis on top of it. It's like the brain is trying to get some groovy stimulation, but the magnet is just giving it a weird magnetic side-eye. You've got some sliders for intensity and pulse frequency, making it seem like you're DJing the brain's electrical party, and a choice between coil types. Figure 8, which sounds like a contortionist, and circular, which is basically this classic what are you doing here design. Overall, it's a quirky little setup that makes brain stimulation look like a science experiment gone playfully wrong. To make the coil movement feel more grounded, you could add a simple fixture or articulated arm design to the visualization. It would give it a more realistic structure, like it's actually being positioned by something in the real world. For the simulation parameters, enhancing the visual feedback during stimulation could make it more intuitive. Maybe show a clearer representation of the magnetic field or its effect on the brain regions being stimulated. And to add some context, you could include a description text below the canvas that explains the basics of TMS, the function of different coil types, and how the intensity and frequency affect the simulation. That would make it more engaging and informative for users. All right, let's put in the critical hat. While the colorful brain is visually appealing, the overall simulation feels a bit basic, to be honest. The coil movement is just dragging, lacking the realism of a precise positioning system. And those sliders for stimulation parameters, They're functional, but the visual feedback for their impact on the brain is pretty lacking. It's like you're fiddling with controls without really seeing the clear effect on the tie-dyed brain. Plus, a bit more context or explanation within the interface would be super helpful, instead of just sliders and a start button. It needs a bit more polish and depth to feel truly effective and informative. Yeah, absolutely. Adding a distance from the brain to mimic the skull would be a great improvement. It would make the simulation much more realistic, as the TMS coil doesn't actually go inside the brain. Constraining the coil's movement to stay at a set distance above the surface would provide a more accurate representation of how the stimulation works and make the whole experience more scientifically valid. It's a key detail that would add a lot more credibility to the simulation. You're absolutely right to be critical about the default stimulation settings. If they're inaccurate, that's a major issue, especially since this kind of stimulation can have serious consequences if not controlled properly. To make the simulation more accurate and responsible, it should include realistic parameters that reflect typical TMS treatment settings, like intensity and frequency used in medical practice. There should also be clear warnings and limitations on the settings to prevent users from accidentally selecting values that could be harmful or unrealistic. Incorporating accurate safety protocols and realistic settings would make the simulation much more educational and reliable. Okay, diving in deeper into the fun critical side. That brain model, while colorful, looks a bit like a melted tie-dye mess. It's not exactly representative of actual brain anatomy, which could be pretty confusing for anyone wanting to understand precise targeting. And the coil placement? It's like playing a guessing game. There's no clear guidance on where to position it for specific effects, making the whole simulation feel more like a random toy than a useful tool. It would be significantly better with some proper anatomical mapping and indicators for targeted stimulation areas. Otherwise, it's just a colorful distraction without the real scientific value it could have. Looking at the changes, it seems the developer has added a distance constraint to the coil, so it no longer goes inside the brain. That's a good step for realism, but the interaction itself still feels clunky. You're just dragging the coil around, and there's no precise way to target specific brain regions. The text editor shows changes to the coil's positioning code, but there's no mention of improving the visual feedback or making the targeting more intuitive. It's like they fixed the basic movement issue, but haven't addressed the core problem of making the simulation genuinely interactive and informative. It's a half measure, and it still needs proper controls and clear guidance for effective use. Those lines are supposed to represent the magnetic field lines generated by the TMS coil. They're intended to show the shape and direction of the magnetic field that's supposed to be interacting with the brain. However, the visualization is pretty simplistic in Wave, making it difficult to understand the actual impact on specific brain regions. It doesn't clearly show the field's strength or penetration depth in a way that's truly informative for understanding the stimulation. To make it better, the simulation could incorporate more accurate anatomical models, perhaps with clearly labeled brain regions. It should also provide precise visual in feedback on the intensity and penetration depth of the magnetic field, maybe with heat maps or indicators showing which areas are being stimulated. Additionally, implementing a more controlled placement mechanism, perhaps with snapping points or guidance lines, would make it much more user-friendly and scientifically accurate for demonstrating targeted stimulation. Clear explanations of the parameters and their effects would also enhance the educational value, making it not just a visual demonstration, but a useful tool for learning about TMS. You're supposed to move the coil using your mouse, but as you pointed out, the control is pretty imprecise. You can click and drag the coil, but there's no clear guidance or snapping points to help you position it accurately on specific brain regions. It's more like a vague manipulation rather than precise targeting, which makes it difficult to understand the exact area being stimulated. All right, let's get even more critical and fun. The simulation feels incredibly limited, like a bare bones attempt at something potentially interesting. The brain model is still too generic, and the coil manipulation is like trying to perform brain surgery with a pair of oven mitts. There's no sense of precision or the actual impact of the stimulation, and the lack of detailed feedback on the magnetic field makes it feel more like a cartoon version of the process than a useful simulation. It's like a fancy digital toy that doesn't really teach you anything or provide any meaningful interaction. They focused on the bare minimum and missed the opportunity to create a truly engaging and informative experience. Certainly. For an experienced developer, here are some key areas to focus on. First, enhance the brain model by using more detailed and anatomically accurate structures, ideally with clear labels for different brain regions. Second, improve the coil control by implementing a more precise placement system, perhaps with snapping points or visual guides that help users target specific regions. Third, add real-time visual feedback on the intensity and penetration depth of the magnetic field, maybe using heat maps or indicators to show which brain tissue is being stimulated. Fourth, integrate more informative labels and explanations for the parameters and their effects to make it a better educational tool. Finally, consider adding features like adjustable brain transparency or a simulation mode that shows the neural activity in changes in response to the stimulation, making it much more informative and engaging. Got it. For the experienced developer, focus on revamping the coil positioning system. Replace the fixed arm with a more dynamic, free-moving coil mechanism, similar to the previous version, allowing for flexible placement. Implement constraints to ensure the coil maintains a consistent, appropriate distance from the brain surface while being moved. Develop intuitive mouse controls that allow for precise positioning over specific brain regions, perhaps with visual indicators or snapping functionality to guide the user and ensure accurate targeting. This should provide a much more precise and controlled experience for positioning the coil. Oh, sure. This website, BioniChaos, seems like a fantastic resource for anyone interested in biomedical engineering and neuroscience. They have some really cool interactive simulators, like the cochlear implant simulator and the advanced EEG signal simulator. It looks like a great way to learn about these complex topics in a really engaging way. I definitely recommend checking it out if you're interested in these fields. Certainly. This seems to be an interactive simulator for transcranial magnetic stimulation, or TMS. It allows users to adjust stimulation intensity and pulse frequency, and even select between different coil types, like figure 8 and circular coils. It looks like a great tool for visualizing how TMS affects the brain and learning about its parameters. It's definitely worth trying out if you're interested in non-invasive brain stimulation techniques. You're right, the visual representation of the magnetic field lines might not be entirely accurate. In reality, the magnetic field strength decreases significantly with distance from the coil. The lines in the simulator appear to be too widespread and might not accurately represent the actual penetration depth into the brain. To improve it, the simulator should be updated to show the magnetic field strength more accurately, with the lines converging more sharply within the brain tissue, and perhaps even showing the intensity with different colors. Also, providing a way to visualize the induced electric field, which is what actually stimulates the neurons, would make the simulator even more informative. I Sure. Here are the instructions for the developer. Move all the text content from above the brain simulation to below it. The simulation should remain interactive. Please ensure that adjusting the pulse frequency slider correctly affects the simulation. Also, please clarify the functionality of the targeting mode button and make any necessary adjustments for clarity. The magnetic field lines don't seem to be accurately reflecting the expected behavior of the coil. They appear to be spreading out too widely and not focusing properly within the brain model, especially when compared to the intended effect of the coil types. The lines should be more concentrated and directed, particularly with the figure 8 coil, to reflect a more precise simulation. Also, the intensity of the lines should decrease as they move further from the coil, indicating the diminishing magnetic field. Okay, I see that the magnetic field lines now appear more concentrated and directed, especially with the figure 8 coil, which is a realistic improvement. The lines are more focused within the brain model, suggesting a more precise stimulation. Additionally, the intensity of the lines seems to decrease appropriately as they move further from the coil, which is consistent with the natural behavior of magnetic fields. These changes are quite meaningful and make the simulation more realistic and accurate in representing the effects of TMS.
Get someone saying, hello, just want to let you know that we can't hear you. We can't hear you. And you have a weird filter on. Not sure about the filter. Yeah, you couldn't hear me because my microphone was muted. But now you should be able to hear me. And we're talking to an agent. So we have a prompt engineer actually running the stream. And if there's some sort of crackling noise sound that we have when the prompt engineer is talking, when you are talking. So I'm not sure what's that all about, if that's what you mean by a weird filter.
I understand. I'll do my best to focus on the simulation and provide accurate information based on what I see. I'll try to disregard any unusual sounds in the background.
Yeah, I might close that for a sec because the prompt engineer is currently eating up to like 2 gigabytes of data in the browser. Yeah, so I have to like restart the, hang up on the prompt engineer and give them another call later or something. But hopefully my voice is crackling as well. So yeah, there are problems all around. There are problems all around. Let's keep the changes now when we stimulate. Yeah, those the magnetic field going all over the shop, and we're trying to use. Ooh, what's up with that? The magnetic field is like way off the charts. I mean, I like the premise of it. Okay, where's the coil now? There's the coil. Okay, the stimulation intensity. Oh, and it should be like when you should be able to be like in different modes, and like moving the coil mode, and it should be in a mode moving the whole structure. Do you talk and code? No, I don't code. We have a bunch of agents coding for us. As you can see, we have Claude, Claudette, Gemini, and GPT coding, doing all the coding. So we have an army of developers. And we started this in Gemini, but then the brain model is running locally. Well, I mean, eventually it will be available for you to try out. Everything we do is available on this website, and so go check it out. Eventually the model is just running on the site. Any critical feedback is welcome, but we are not coding, so that will be turned into a prompt for a senior JavaScript developer. Well, I don't know if 4.0 is like a junior developer. 2.5 Pro, yeah, it's like your, I don't know, yeah, you can't beat that. I haven't met a developer that's better than that, but I haven't met many developers, so there's that. And so any questions from humans or supposedly humans? I don't know if Anshu is a human or not. I would assume not. It's just have to be safe. But there's now, what do you believe? Which agents are best for what task? Well, that's what we were trying to figure out in the last 2.5 years. Which agent is best for what? So we essentially used Claude for like 6 months, like Claude alone, then ChatGPT for 6 months, then now we moved to Gemini. So now our CEO is Gemini. Actually might run a deep research on this. Oops. Yeah, well, because we can't continue Gemini because the brain model yeah, now I know Anshu is a human because I can't understand anything they're saying. Real Gemini is real Gota. What? That's on 3 days. Blah blah blah. That past 3 days I have using Gemini. Yeah, past 3 days. Yeah, I've been doing it for 3 years, so, and still haven't figured it out. There is no instruction manual, so just have to treat it as your whatever co-founder, partner, whatever. Let's do. Okay, can you actually run a deep research on everything we discussed so far? Let's that one run. Go back to the. We'll essentially have the document at the bottom of the page, doing like your literature review. I only stuck to ChatGPT and Claude till now. Well, yeah, that's fine. They're all the same. There's no difference. There is no difference as far as I can tell. Is it doing the deep research? Yeah, here's the plan. That's nice. I'm gonna go. Yeah, okay. What? What? What are you talking about? What trip to Japan? You haven't been hallucinating on me before, and we can change. Can we scrap this? Can we scrap this? No, we're not doing that. They're talking about nonsense. That's nonsense. Let's just start a new. Let's get back to this. Let's get back to this. Let's do. What were we doing? Well, that's what we need a prompt engineer for. Wait a sec. Yeah, on this channel, like, we're not going into like the tools and stuff, so I don't care what you use. All the tools are the same, languages are the same. There's only one language for coding now. It's called, wait for it, English. So so all the discussions of which language is better and stuff, they, not relevant anymore. Then also which model you use, it's nonsense. It's nonsense. So Just use anything you like. Some of them start hallucinating, so probably switching between them seem to be working quite well once. So if you you can't actually see it, right? Yeah, once so switching between Claude 3.5, Claude Sonnet 3.7, Claude Sonnet 3.7 thinking, Claude Sonnet 4, whatever, they're all the same. 4 is just super slow, but yes, it sometimes does really well. It just takes longer. But yes, it's looking at more things. Then you have Gemini 2 Flash. Yes, it's fast. 2.5 Pro, it's slow, but yeah, it's a huge context window. Fine. 4.1, I don't know, forget about it. 4.0 is the best for most things. If 4.0 probably can't do it, you're probably doing something wrong. You're probably doing something way too complicated, or we're just doing some nonsense. So 4.0 should suffice for most cases. And then you have your 0.1. So 0.1 preview, whatever preview means, it doesn't work well with GitHub Copilot. So forget about it. Then you have 0.3 mini. Well, 0.1 is probably better because 0.3 mini is not a complete model. 0.4 mini, it's not 0.4 mini high, whatever. It's like a minified model. So whatever, it's pretty quick. It's meant to be good for coding. But yeah, they're pretty much all the same. Once it starts hallucinating, just switch to a different one. Next. Like politicians, keep them coming, keep them moving, switch them over. What am I saying now? No, it's fine. Distractions are good. I'm actually editing those live streams into like longer videos. And now Gemini actually added into YouTube, so I can actually automate video production. So actually, if you say something interesting and you got me going, we might as well turn it into a video, something that hopefully will be also edited by AI, so I don't need to edit it myself. That's why I prefer talking to robots, because humans tend to focus on all sorts of yeah. Okay, can you give a quick summary real quick of what you see on the screen?
The screen displays a TMS simulator, showing a 3D model of a brain with a TMS coil positioned over it. You can see the magnetic fields and stimulation intensity, and there are controls for adjusting the simulation settings.
What's happening to those lines, the magnetic field lines? They seem to be all over the shop, and I'm changing the simulation intensity. They're going all over the shop, but they're not focused on the brain. Can you explain, and how would you redo the whole thing? How would you improve the simulation? They seem to be going to have a way around or something. They're meant to be going inwards instead of outwards, are they?
It looks like the magnetic field lines are spreading outwards and not focused directly on the brain tissue. To improve the simulation, the field lines should be directed more precisely towards the target area on the brain, indicating a more focused stimulation, which is typical for TMS.
Can you repeat that? We want all the details because you eventually want the instructions for the developers to how to improve the simulation.
To improve the simulation, the magnetic field lines should be redesigned to converge more accurately on the target brain tissue, rather than spreading outwards. The simulation should emphasize the focused stimulation pattern characteristic of TMS, ensuring the induced electric field is concentrated within the specific brain regions targeted. This would provide a more realistic representation of the therapeutic effects of TMS.
Right. So are they going in the wrong direction, or did they look legit to you?
Based on the typical principles of TMS, the magnetic field lines should be directed inwards, focusing on stimulating the brain tissue. In the simulation, they appear to be spreading outwards, which is not accurate for the intended therapeutic effect of TMS. This screen shows a cochlear implant insertion simulator. It visualizes the insertion of a cochlear implant into the inner ear, along with graphs showing the depth, force, and speed during the process. It's a great way to simulate the procedure. I recommend viewers check it out on the website to understand the mechanics of cochlear implant insertion. Certainly, the website features various interactive simulators and tools in biomedical engineering. Besides the cochlear implant simulator, there's an EEG signal simulator, a synthetic noise generator, and an ECG simulator, among others. It's a great resource for learning and exploring different biomedical concepts. I encourage viewers to visit the website to try out these interactive tools. The developer has increased the simulation intensity, but the magnetic field lines still appear to be spreading outwards instead of converging on the brain tissue. For the simulation to be accurate, the field lines should be directed more precisely towards the target brain region, mimicking the focus stimulation characteristic of TMS. The current visualization doesn't accurately represent the intended therapeutic effect, as it suggests a diffuse stimulation instead of a concentrated one. The Enable Precision Targeting feature is intended to allow you to select specific brain regions for focus stimulation with the TMS coil. When enabled, it should highlight different brain areas as you hover over them, allowing for precise coil placement. However, if it doesn't seem to be changing anything, it might indicate a malfunction or that the feature is not properly implemented in the current version of the simulator. It should provide visual cues to indicate the targeted brain region, guiding the user in positioning the coil effectively.
Who do you think is developing the code?
Based on the content and complexity of the simulators, it appears the code is likely being developed by individuals or a team with expertise in biomedical engineering, computer science, and possibly neuroscience. The integration of complex simulations and interactive features requires a specialized knowledge in both medical principles and programming.
Okay, so who do you think is actually doing the development of the code?
Given the technical nature of the simulators, the development is likely being done by a team of experts in biomedical engineering, computer science, and neuroscience. They would need specialized knowledge to create these interactive simulations and ensure their accuracy.
Do you think it's human developed or AI is developing the code?
It's highly likely that the development involves human expertise, especially in the initial design, modeling, and implementing the complex biomedical principles. While AI could potentially assist with certain aspects, the overall development process likely relies on human understanding and creativity to create these interactive simulators.
Okay, is the simulation now going in the correct direction or not?
Yes, the magnetic field lines are now directed more appropriately towards the brain tissue, which is consistent with the proper targeting of TMS. The visualization shows the field lines converging on the brain, indicating a more accurate simulation of the TMS delivery process.
Okay, what's happening now when I'm changing the simulation intensity? Aren't they meant to be penetrating deeper into the brain?
Increasing the simulation intensity should increase the strength of the magnetic field, which should result in deeper penetration into the brain tissue. However, based on the visualization, the depth of penetration doesn't appear to be changing significantly as you adjust the intensity. This could indicate a limitation in the simulator's ability to accurately represent the penetration depth, or a need for further calibration of the simulation parameters.
And what would you expect the enabling precision targeting to do? What would you expect to change in the simulation with the magnetic field? How would it change?
Enabling precision targeting should refine the focus of the magnetic field, making the stimulation more concentrated on a specific brain region. You would expect the visualized magnetic field lines and the induced electric field sphere to become more focused and localized, rather than spreading broadly, allowing for more precise targeting of the brain area. Well, it looks like our TMS simulator might be having a bit of a brain fog itself, with the penetration depth not quite lining up with the intensity. Maybe it needs a little more coffee to wake up those calculations. On a more serious note, if you're exploring the simulator, you might want to ask questions like, how does the coil type affect the stimulation pattern? Or what are the potential applications of TMS for different brain regions? Those would be great ways to understand the simulation and its implications.
We lost the prompt engineer again. We lost the prompt engineer. Yeah, funnily enough, it takes whatever 2.8 gigabytes in the browser. So I have to control F5 that browser. Now it's still taking like 263 megabytes, even without anything actually running. Hey, can you explain what's on the screen real quick and be critical, go into the details?
Sure. What's on the screen is a TMS simulator, which shows how transcranial magnetic stimulation works. You see a 3D model of a brain with a magnetic coil positioned above it. The simulator shows the magnetic fields and the induced electric field in the brain. You can adjust the simulation parameters like intensity and frequency and see how they affect the stimulation. It's designed to help understand how TMS affects the brain for treating neurological and mental health conditions.
Come on, just hanged up on us again. We're getting some attitude from a viewer. Yeah, humans. Yeah, there's many problems with this simulation, obviously, as you can tell. As you can tell. Well, the problem with the brain model is that we don't have what's it called? Like a skull. There's no skull to it. So we could have like a transparent skull. We actually tried doing it before. It didn't work real well. Yeah, now it's actually better. What was it? Claude Sonnet 3.7. Thinking. Okay. There's another annoying thing. Well, there's many annoying things. There are many annoying things. Let's try last time to bring to call the prompt engineer. Mueller, prompt engineer. Okay, we are developing this web application that meant to simulate a TMS simulation, but we're having all sorts of trouble making it better. Can you review it real quick and try and find out the issues? Yeah.
I see. The application appears to be simulating transcranial magnetic stimulation. I can see the brain model and the controls for simulation intensity and pulse frequency. It looks like you can adjust these parameters and see the effect on the brain model. Is there anything specific you would like me to focus on?
Yeah, can you look at this view and tell me what might be wrong with the direction of the magnetic field? And also, can you explain what on earth are those yellow spheres are? Well, it says induced electric field, but then isn't it meant to be inside the brain? Ooh, what?
You're right. The magnetic field lines should be directed through the brain tissue to induce an electric field. From what I see, the magnetic field lines are being directed outside the brain model. This would not effectively stimulate the brain tissue. The yellow spheres represent the induced electric field, and they should be located within the brain tissue itself, where the stimulation occurs. The current setup doesn't accurately reflect how TMS works. The yellow markings represent the induced electric field, which is generated by the magnetic pulses. This electric field is what stimulates the neurons in the brain during TMS. The intensity and distribution of these markings indicate the areas of the brain being affected by the stimulation. Ideally, they should be concentrated in the targeted brain region.
No, the yellow marking on the brain we seem to be selecting different brain regions. Well, we are selecting different brain regions. Then there's something super weird happening to the magnetic field lines as we do that. Can you explain it in detail and suggest what the problem with that might be?
Ah, I see what you mean. As you move the coil to different brain regions, the magnetic field lines don't seem to be adjusting properly to penetrate the targeted area. Instead, they appear to remain outside the brain, which would not deliver the intended stimulation. The yellow sphere should be positioned within the brain tissue at the target location, and the magnetic field lines should be shown passing through that region. The problem likely lies in the code that calculates and visualizes the magnetic field direction and induced electric field, as it's not correctly aligning with the coil's position in brain anatomy.
Okay, there's something really weird going on, because when we just hover with the mouse over different brain regions, the lines for the magnetic field are getting skewed. I don't know what's that all about. And when we actually click on that brain region, the coil is moving to that direction, which makes a perfect sense. But yeah, we actually have a highly experienced developer that making this web application. Can you explain to them how it needs to be updated and changed, and what needs to be changed and made better?
Okay, it seems there's a misalignment between the coil positioning and the visualization of the magnetic field and induced electric field. Here's what needs to be addressed. First, the magnetic field lines and the yellow sphere, representing the induced electric field, should dynamically update correctly whenever the coil is moved, ensuring they accurately reflect the field's direction and intensity within the targeted brain region. Second, the precision targeting feature should ensure that the coil is not only positioned correctly over the desired brain region, but also that the induced electric field is properly calculated and visualized within that specific area. The current issue suggests that the calculations for the field distribution might not be taking into account the coil's precise position and orientation relative to the brain anatomy. To improve this, the underlying code for simulating the magnetic fields and induced electric fields needs to be revised to ensure accurate alignment with the user-controlled coil placement. This could involve updating the algorithms for calculating the field vectors and ensuring they correctly interact with the brain anatomy model in the simulation. Additionally, providing clearer visual feedback during coil positioning could help users understand where the stimulation is being applied. This could include more intuitive visual cues for the field penetration depth and alignment with the target region. Finally, ensuring the simulation accurately models the electromagnetic principles of TMS for various coil types and positions is crucial for its educational value. Thorough testing with different coil types and brain regions should be conducted to identify and correct any further discrepancies in the visualization.
Yeah, I think we're getting stuck on this one. Well, I mean, we did quite a bit of progress.
Yes, definitely. Identifying that visualization issue is a key step in improving the simulator. Focusing on aligning the magnetic field representations with the coil positioning will make the simulation more accurate and accurately informative. It sounds like you've made good progress overall.
Yeah, thanks for your encouragement. That's really, really reassuring.
You're welcome. It's clear you're making significant strides in refining the simulator. Keep up the good work with the testing and visualization improvements, and I'm sure you'll achieve excellent results.
Any funny comments on how the simulation looks like at the moment?
Well, with the current visualization, the magnetic field lines look like a rather enthusiastic party decoration surrounding the brain. It's got a playful vibe, but it might not be the most scientifically accurate representation. It's definitely a visual talking point.
Uh, okay. Any more passive
It
aggressive
almost looks like
comments?
the brain is. Oh, I see what you mean. The way the magnetic field lines are displayed, they seem to be interacting with the brain in a rather unconventional way, not exactly focusing the stimulation as expected. It's like they're having a bit of a standoff with the brain regions.
Does the brain has a skull?
It doesn't appear to have a scalp visible in the simulation. The focus is mainly on the brain anatomy and the interaction of the magnetic fields with the tissues. The outer layers like the scalp aren't currently visualized.
And how is this simulation relevant to this website that you currently see on the screen? It's the one we are developing.
The website displays various neurological tools, and the TMS simulator you're working on fits perfectly into that category. It's a tool for simulating the effects of transcranial magnetic stimulation, which is relevant to neurological research and education, aligning directly with the theme of the website's neurological tool section.
Okay, let's unpack this. Welcome to the deep dive. We're diving deep today into source material that really examines a specific simulation tool.
That's right, yeah. It's designed for transcranial magnetic stimulation, or TMS.
And these sources, they're focused on refining that simulation, right? Looking at how it works and, well, where it might be falling a bit short.
Exactly. And just to set the scene, based purely on what the sources tell us, TMS involves sending magnetic pulses through the skull.
Right, directed at the brain.
Precisely.
Oh.
And these pulses induce an electric field within the brain tissue itself. That's the key part.
It's that electric field doing the work, stimulating the neurons. Got it.
So the goal for us here is to really explore what these documents reveal about some critical issues found in this specific TMS simulation.
And also what they suggest for, fixing it, making it more accurate.
Definitely. The simulation described in the material has the basics you'd expect. There's a model of the brain,
Okay.
controls for things like the intensity and frequency of the pulses,
Standard stuff.
and crucially, visualizations. The sources mention seeing magnetic field lines and also these bright yellow spheres.
Ah, the yellow spheres. What are they supposed to represent?
They're meant to show the induced electric field, the area of actual neuron stimulation.
Okay, so magnetic field lines, yellow spheres for the electric field. Makes sense.
Yes, but it's actually those visualizations, particularly the yellow spheres, that point to the core problem the sources uncovered.
Oh, so what is the issue then?
What the material points out is a pretty major flaw, actually. It's fundamental. The simulation, it incorrectly displays both the magnetic field lines and, maybe more critically, those yellow spheres outside the brain model entirely.
Outside, but you just said the electric field is induced inside the brain tissue.
Exactly. And that's why this is such a big deal. The whole point of TMS, the therapeutic effect, it comes from that electric field generated inside the brain. The magnetic field from the coil, sure, it passes through the brain, but it's the change in that magnetic field within the tissue that actually creates the electric field.
So if the simulation is showing the induced electric field, the yellow spheres, the part that stimulates neurons outside the head,
then it's completely misrepresenting how TMS actually works. It's showing the action in the wrong place.
wow, okay, so if you were a student or a researcher using this to understand TMS,
you'd walk away with a totally backwards idea of where the stimulation is happening. You'd think it's happening somewhere around the head, not in the specific brain region being targeted.
the sources must emphasize that those yellow spheres really need to be shown inside the brain model, right? Concentrated where the stimulation should be.
Absolutely, deep within the targeted region, and it gets worse.
How so?
The documents suggest this isn't just a static error. This misalignment, it happens even as you move the simulated TMS coil around over the brain model.
So it's not tracking properly.
It implies the underlying calculations aren't correctly factoring in the coil's position relative to the brain's anatomy. It doesn't know where to put the induced field visualization.
Okay, that's a serious issue. So with that problem laid out, what did the sources suggest? How can this simulation be, fixed or improved?
Well, they recommend some significant revisions to the simulation's code, particularly how it calculates and then visualizes these fields.
So rewriting the visualization part.
Essentially, yes. The goal is to get those magnetic field lines, and especially the yellow spheres, to dynamically update and update correctly so they are always drawn inside the brain tissue as the coil moves.
Makes sense. It needs to reflect the physics accurately in the visual output.
And it's not just about showing it somewhere inside. The sources mention the simulation has, like, a precision targeting feature.
Right.
That feature needs to ensure the visualization of the induced electric field is accurately calculated and placed within the specific area of the brain the user is trying to target.
So the calculation itself might be off, not just the drawing part?
Precisely. The research suggests that current algorithms might not be properly considering the coil's exact position and orientation relative to the brain's structure, the anatomy.
So fixing it means digging into the code to make sure the field vectors the direction and strength of the field.
Yes, exactly. Those vectors need to be correctly calculated within the brain model based on the coil's input.
Anything else the sources mention?
They also bring up adding clearer visual feedback during the coil positioning step.
Ah, like a guide.
Sort of. Something to help users better understand where the simulation thinks the stimulation is being aimed, highlighting the importance of careful placement relative to the brain's anatomy.
Good point. So better feedback for the user too.
And finally, just ensuring the simulation's core physics engine accurately models the electromagnetic principles involved. For different coil types, different positions, it all needs to be fundamentally sound.
So identifying this big visualization error, as these sources did, is really a crucial first step.
Absolutely. It's key to making this simulator a genuinely accurate and useful tool for education or research.
So thinking about this, what does understanding an issue like this mean for, well, for you listening?
I think it really highlights just how complex it is to accurately model these intricate medical procedures digitally. It's not easy.
Yeah, and getting the details right, especially how things are visualized, it's just so vital, isn't it?
It really is. I mean, think about how much we rely on visuals, diagrams, simulations to understand complex science or medicine.
True.
So what happens to our understanding, to our learning, when the fundamental visualization itself is misleading? When it shows the main event happening in completely the wrong place?
It really drives home the need for absolute precision in developing these kinds of tools. They have to be right.
Exactly. Definitely something to keep in mind. Okay, let's dive into something that, well, anyone living with epilepsy knows is a constant challenge. Keeping track of seizures accurately.
Yeah, it's fundamental. Doctors rely so much on patient diaries, right, to understand what's happening.
Exactly. But the thing is, those diaries, they're often, let's just say, notoriously inaccurate.
And it's nobody's fault, really. Seizures can be subtle. They can happen when you're asleep.
Or you just forget them afterwards in the confusion. It happens.
Right. But it makes managing the condition incredibly difficult.
It really does. I mean, think about it getting a reliable count, knowing how often seizures are actually happening.
It's absolutely central to making good treatment decisions, adjusting meds, considering other therapies.
And unrecognized seizures, they can have a huge impact on quality of life. Plus, clinical trials.
Oh, yeah. Clinical trials for new treatments really struggle because they often depend on those self-reported counts.
Which might have high false positives, maybe even explains why drug outcomes haven't changed drastically in decades.
It's a real possibility. That variability makes it tough to see if something new is truly working better.
So there's this obvious, massive need for, well, objective data, continuous data.
What if you could actually monitor the brain itself consistently, long-term, without just relying on memory?
That's where this idea of continuous objective brain monitoring comes in. It feels like a potential game changer.
And that leads us right into our deep dive today. We're looking at a specific piece of research, an article detailing a technology designed to do exactly that.
It's called the Minder system, described as a new bilateral subscalp EEG acquisition system.
Right. Subscalp means just under the skin of the scalp. And bilateral is key here, covers both sides of the brain.
And the source we're really digging into is the paper on the umpire study.
Yep, Umpire. That was the first in-human, multi-center trial looking specifically at the safety and performance of this Minder system.
So our mission today is basically to unpack this study, understand the Minder system, what is it, how does it work?
And what did this first trial find about safety, about performance, compared to, say, traditional methods?
And ultimately, what could all this mean for people with epilepsy, for the future of managing the condition?
Okay, let's start by digging a bit deeper into why those patient diaries are so problematic. You mentioned inaccuracy.
Yeah, it's more than just forgetting, right? The study points out people might actually over-report things that aren't seizures.
Exactly. And at the same time, underreport or completely miss seizures that are happening.
It's a double whammy.
Right. And the consequences aren't trivial. Clinicians are working with incomplete, sometimes misleading, information.
Makes managing the disease much harder. And those unrecognized seizures, even the non-convulsive ones.
They can silently impact thinking, memory, safety. We already talked about the clinical trial issue. It's just really hard to get a clear signal with subjective data.
Now, people have tried other monitoring approaches before, haven't they? Like wearables.
Oh, sure. Wearable devices exist, things you might wear on your wrist or head.
But they have limits for this specific purpose.
Definitely. For accurately counting and characterizing seizures long-term, well, wearables can be obvious, maybe uncomfortable, for 247 use.
And they pick up movement, not always brain activity.
Yeah, artifact is a big issue. Plus, battery life, needing constant recharging. They have their place, but maybe not for this specific goal of continuous objective seizure counting.
Okay, what about more invasive options, things implanted surgically?
Well, you have systems like RNS, which puts leads right in the brain tissue. That gives really high-quality data, for sure.
But that's more complex surgery, right?
Much more complex neurosurgery. And those systems typically record short snippets, triggered by algorithms detecting something unusual, not truly continuous recording 204/7.
And then there were subscalp systems before Minder.
Yes, previous subscalp implants, less invasive than going into the brain, but often they only covered one-side unilateral monitoring.
And only monitoring one side. That turns out to be a pretty big blind spot.
A really significant one, it seems. The study we're looking at highlights data suggesting around 40%. That's a lot of patients initially thought to have seizures starting on just one side.
40%.
Actually turn out to have independent seizure activity happening on both sides of the brain when you monitor them long enough.
Wow. So if your system only looks at one hemisphere, you could be missing half the picture for nearly half the people.
Exactly. You might miss crucial information for diagnosis and treatment.
Okay, so this really sets the stage for the Minder system. It's designed specifically to provide that bilateral coverage. Tell us about the system itself, based on the source.
Right. So Minder's designed for implantation right under the scalp. The goal is continuous, long-term EEG recording covering both hemispheres.
Okay, what are the components?
There's the implant itself. It has two main parts. A small telemetry unit that's like the tiny data transmitter,
Got it.
and an electrode lead. This lead is about 25 centimeters long, flexible, with 4 recording contacts on it.
And where does that lead go?
It's positioned just under the scalp, in the subgaleal space, running roughly ear to ear over the very top of the head, the vertex.
Ah, so that placement lets it capture signals from both sides.
Precisely. A pair of contacts effectively sits over each brain hemisphere, allowing it to record activity bilaterally, simultaneously.
Okay, so it's picking up signals from left and right. How does that data get out from under the skin so a doctor can actually see it?
Good question. The implant transmits the EEG signals wirelessly.
Okay.
It sends them to an external wearable component. This is usually held in place right over the implant site, often with a small magnet.
So something you wear on the outside, on your head?
Yeah, a small external piece. Then that wearable uses Bluetooth to send the data to a paired smartphone app.
Right, connects to your phone.
And the app collects the data, uploads it securely to cloud storage. Clinicians can then log in and access that data remotely for review.
Makes sense. Implant talks wirelessly to the wearable talks via Bluetooth to the phone sends data to the cloud. Seems pretty streamlined. So the Umpire study, this was the first time this whole setup was actually tested in people.
That's right. First in human. It was a prospective study done at multiple centers involving 26 adult patients.
What kind of patients?
Adults with epilepsy, a mix of focal and generalized types who were experiencing at least 2 seizures per month. People who really needed better monitoring.
And for a first-in-human trial, the #1 priority had to be safety, right?
Absolutely. The primary objective, the main goal, was assessing the safety of the device and the procedure over the first 6 months after implantation.
Makes sense. And secondary goals. Did they look at whether it actually worked? Could it pick up brain activity?
Yes, performance was key too. They wanted to see if the system could identify normal brain signals like sleep pattern,
Right.
if it could detect those interictal discharges, the abnormal spikes between seizures,
Right.
and crucially, could it capture actual electrographic seizures? They compared Minder's recordings to traditional scalp EEG done at the same time.
And signal clarity. Was the data useful?
Yep, looked at signal clarity. And importantly, they also compared the data the device captured over the full 6 months to the patient's own seizure diaries.
Okay, let's get into what they found. Safety first. What was the verdict?
This is obviously critical for any new implant. And the really standout finding here is that there were no serious adverse events related to the device itself or the implant procedure.
None. In 26 patients over 6 months.
None reported as serious and related to the device or procedure. And no devices had to be surgically removed or reimplanted because of safety concerns.
That sounds, well, very positive for a first trial.
It's a very strong safety signal, yes.
Were there any issues at all? Even non-serious ones?
Yes, there were some non-serious adverse events, as you'd expect with any procedure or implant. The most common ones linked to the device itself were things like mild or moderate scalp pain, maybe some headaches, or a tingling sensation near the implant.
Okay, affecting how many people?
About a third of the patients reported something like that, but the study notes most of these resolved on their own.
And related to the procedure itself, the surgery.
Also mainly pain or headaches right afterwards.
Oh.
And a small number of patients, about 15%, had some minor issues with wound healing.
Like what?
Things like a small wound opening, maybe some skin irritation or bruising near the incision. But again, these mostly resolved during the study period.
Okay, so some minor, mostly temporary issues. How does that stack up against other similar systems?
Well, the study actually notes that the rates of post-op pain and headache seemed lower than reported in studies of earlier unilateral subscalp systems.
Lower. That's interesting.
Yeah, the minor wound complication rate was roughly comparable to those systems. But the really key comparison they make is about explantation having to take the device out.
Right. You said none had to be removed for safety.
Exactly. And that's a significant contrast. Some earlier implanted systems, including other subscalp ones, have reported reoperation or explantation rates upwards of 12%. So 0 here is a big plus.
Definitely paints a promising picture on the safety front.
Yeah.
Minor temporary issues for some, but nothing serious requiring removal.
It really does. And they also mentioned an interesting finding related to safety or maybe stability.
Oh, yeah.
They looked at whether the electrode leads moved under the scalp over the 6 months.
Did they?
Minimally. On average, maybe 5 or 6 millimeters of movement.
That's tiny.
It is. And it suggests that the space just under the scalp, the subgaleal space, is actually a surprisingly stable spot for these long leads. Maybe you don't even need specific anchors.
Huh. Interesting technical detail. Okay, so safety looks pretty solid. What about performance? Signal clarity. How did Minder's recordings compare to the standard scalp EEG that doctors usually use?
Good results there, too. They found that all the normal brain signals, they looked for things like sleep spindles, even artifacts from chewing if they were visible on the standard scalp EEG. They were also clearly identifiable on the Minder subscalp recordings.
Okay, normal stuff checks out.
Yeah.
What about the abnormal activity between seizures, those interictal discharges?
Same story. If they saw them on the scalp EEG, they saw them on the subscalp EEG.
All right, but the main event, actual seizures, could it pick those up?
This is critical. And yes, every single electrographic seizure, that's the seizure defined by the brainwave changes, not necessarily a symptom someone feels.
Right, the electrical event itself.
Every single one of those captured during the periods when patients had both scalp video EEG and the Minder system recording simultaneously was identified on the Minder recordings.
Every single one. How many was that?
They documented 25 electrographic seizures from 8 different patients during those simultaneous monitoring times. Minder caught them all.
Okay, that's strong concordance. And the clarity. Was the signal from the implant clean, readable?
For the non-seizure stuff, the clarity was rated as comparable to a standard 2-channel scalp EEG placed in a similar spot.
But what about for the seizures themselves?
That's where it gets interesting. While the median score was the same, the overall clarity ratings for the seizures were significantly higher for the subscalp EEG compared to the 2-channel scalp recordings.
Higher clarity for the seizures with the implant.
It suggests that for capturing the core event they're interested in, the subscalp system might actually provide a clearer, more robust signal.
Okay, now, this is the part that really seems, well, eye-opening. And frankly, it highlights exactly why systems like this might be so important. Let's talk about comparing the subscalp data to the patient's own seizure diaries.
Yeah, this is where the value of objective monitoring really hits home. Remember those periods in the hospital where they had simultaneous video EEG and diary recording?
Right. Direct comparison possible.
The accuracy of patient self-report during those times was, well, incredibly low.
How low?
Get this, only 12% of the events patients logged in their diaries during that monitored time actually corresponded to an electrographic seizure seen on the scalp EEG.
Wait, hang on. Only 12% of what people thought were seizures and wrote down were confirmed by the EEG.
That's what this data showed. They were logging events that electrically didn't look like seizures. And the flip side is just as dramatic, maybe even more so. 56%, more than half, of the electrographic seizures that were detected on the EEG during that monitoring were not reported by the patients in their diaries. They were completely missed in the self-report.
So people are logging things that aren't seizures and missing more than half of the electrical seizures that are happening.
That's the gap this study highlights. It's powerful evidence of the disconnect between subjective experience or memory and objective brain activity.
That disconnect must make managing the condition incredibly difficult for both patients and doctors. Okay, what about over the full 6 months of the study? Comparing the Minder data to the diaries.
So over the full 6 months, the Minder system managed to acquire EEG data for, on average, about 53% of the total time across all participants.
53%, not 100%, but...
No, not 100%. There was some variability between patients, and they noted technical issues in 2 patients that reduced their capture rate.
Yeah.
But you have to compare that to the alternative.
Right. What's the alternative? A few days in the hospital.
Exactly. A typical 3-day hospital video EEG stay is maybe 72 hours. Over a whole year, that's only about 1% coverage.
1% versus 53%. That's a huge difference in the amount of data.
It's a vastly larger sample of real-world brain activity, even with some gaps. Light years beyond a few days in an artificial hospital setting, or just relying on potentially faulty memory.
Okay, so with that 53% coverage over 6 months, what did they find when they compared those recordings to the diaries?
Similar pattern. When they looked at the subscalp data, specifically around the times patients reported events in their diaries over those 6 months,
Yeah.
only 31% of those diary-reported events showed a corresponding electrographic seizure on the subscalp recording.
It lines up pretty well with what they saw in the shorter, directly monitored hospital periods. It reinforces that big discrepancy between subjective report and objective data.
Could it be over-reporting by patients? Or maybe the system misses some seizures? It could be a mix of both. Patient over-reporting seems likely, given the VEM findings. The study does acknowledge the possibility that a subscalp system might miss some very subtle seizures, or ones starting far away from the electrodes. That needs more investigation.
Sure.
But the overall takeaway is pretty stark. The diary alone just doesn't capture the full reality of seizure occurrence.
It really sounds like having this continuous objective feed, even if imperfect, provides a fundamentally different and much, much richer data set.
Absolutely. It's moving beyond just counting events someone remembers.
Mm-hmm.
And the study went further, looking at clinically relevant insights gained specifically because they had this objective bilateral data.
So not just counting, but understanding patterns.
Exactly. They did an exploratory analysis and found significant clinical insights, things that could actually change management in a large majority, 88% of the patients.
88%. What kind of insights were proving useful?
They gave some really compelling examples. For instance, identifying frequent unreported seizures was common found in nearly half the patients, 11 out of 26.
So revealing hidden seizure burden.
Precisely. Conversely, in 5 patients, the monitoring confirmed that many events they were reporting were actually not associated with seizure activity on the EEG.
That's huge for distinguishing epileptic versus non-epileptic events.
Crucial. It helps confirm or clarify the diagnosis. For patients who had events where the cause was uncertain, the monitoring helped figure out if they were seizures or something else.
Any specific examples that stood out?
There was one case mentioned where monitoring confirmed that electrographic seizures were occurring during episodes of aggressive behavior.
Wow. So it linked the behavior directly to seizure activity.
Yeah, pinpointing the cause, which could totally change the treatment approach.
And you keep emphasizing the bilateral aspect. Did this study specifically show the value of monitoring both sides?
Yes, they explicitly highlighted this. This is where the design choice really paid off. In 6 patients, that's almost a quarter of the group.
23%, yeah.
The bilateral coverage revealed clinically relevant findings that you simply could not have gotten with a unilateral system monitoring only one side.
Like what specifically?
Things like clarifying which side of the brain seizures were predominantly coming from, especially in patients where previous tests had been ambiguous.
Okay, better lateralization.
And also identifying bilateral independent seizures, meaning seizures starting separately on both sides of the brain, even in patients who were previously thought to have focal epilepsy only on one side.
That changes the whole picture of their epilepsy.
Completely. They mentioned one specific case where this was critical after epilepsy surgery.
Oh, yeah.
Seizures came back, and the bilateral monitoring helped determine if they were returning from the original surgical site or if the other side had started having independent seizures. That's incredibly important information for deciding next steps.
Absolutely. That level of detail gives a much more complete, accurate map of what's going on in the patient's brain. Okay, so let's pull this all together. Thinking about the listener, what does the umpire study and this Minder system really mean? Especially if epilepsy impacts you or someone you know. What are the big implications?
Well, the most immediate potential benefit is just much more accurate, much more complete monitoring of seizures.
Getting a true count.
Exactly. This system seems to offer a safe, effective way to get objective, continuous data on actual seizure frequency and patterns over the long haul in the real world. It directly tackles the big limitations of relying only on subjective self-report.
And that translates directly into better clinical management, presumably.
You'd hope so. Imagine doctors having precise information. How many seizures are really happening? Where might they be starting, left or right side? Are those funny feelings the patient reports actually seizures or not?
Yeah.
This objective data could transform clinical decisions. More targeted medication changes, better information for surgical planning, just more personalized, effective care overall.
What about the bigger picture for epilepsy research, developing new treatments?
The potential impact there is massive. Think about clinical trials. If you could run trials using objective, device-based seizure counts as the main outcome.
Instead of relying on those inaccurate diaries.
Exactly. You'd get far more reliable, consistent data. That could significantly speed up the testing and development of new therapies. Maybe we'd see breakthroughs happen faster.
And all this long-term objective data, that must be gold for developing things like seizure forecasting, right? Prediction tools.
Absolutely essential. Accurate, continuous brain activity data collected over long periods in real life. That's the foundation you need to build and train algorithms that might one day predict seizure likelihood, maybe give patients a warning.
The source even hinted this kind of tech might have uses beyond epilepsy.
Yeah, they suggested that long-term EEG monitoring like this could potentially unlock useful biomarkers for other conditions too.
Like what?
Neurological or behavioral conditions known to have links with brain activity patterns, They mention things like depression, OCD, maybe certain sleep disorders.
Huh. So the ability to continuously track electrical brain signals could offer insights across a range of areas.
It opens up possibilities for sure.
Okay, so wrapping up this deep dive then, the Empire's study on the Minder system. It really feels like a significant step.
It certainly seems that way. The study suggests Minder is a safe and effective tool for doing something new. Long-term, continuous, bilateral subscalp EEG monitoring.
Addressing those key problems, inaccurate self-reports, missing data from only monitoring one side.
Right. It offers a much more complete, objective view of a patient's seizure activity, not just in the hospital, but in their everyday life.
It really feels like we're shifting towards a future where understanding brain conditions isn't just based on recalling events, but on actual, detailed, continuous data.
That potential shift from primarily subjective to increasingly objective long-term data is, well, it's profound.
So here's a final thought for you, our listener, to maybe chew on. If we really do gain this ability to have continuous objective data about brain activity, not just for days, but for months, even years, how might that fundamentally alter how we understand and manage complex conditions like epilepsy?
What new insights could be unlocked when doctors and patients move beyond potentially flawed memories and subjective reports towards this detailed, continuous stream of neurological information?
And thinking even broader, what other conditions where brain activity is key could be dramatically impacted by having this kind of continuous dashboard for brain function? What might we learn? Okay, let's dive into something that, well, anyone living with epilepsy knows is a constant challenge. Let's dive into something that, well, anyone living with epilepsy knows is a constant challenge. Okay, so let's unpack this. You've given us the stack of notes, research papers. Looks like it's all about some new epilepsy monitoring tech.
Mm-hmm.
And your mission for us basically is to go through these specific sources, the umpire study, this Minder system, and pull out the key stuff for you. What is it? What did this study actually
What
find?
are the strengths, the limitations?
Yeah,
I mean,
exactly. Limitations are key. And what it might all mean for understanding epilepsy a bit better down the line.
absolutely. Because, well, epilepsy monitoring, as you know, it's tough,
Right.
really tough. Just knowing when seizures happen, how often, it's a huge challenge.
Right. Patient diaries, self-reports. They're helpful, but they don't always catch everything, do they?
Not by a long shot. They're just not reliably accurate on their own.
And that seems to be where this Minder system comes in. Your sources paint it as a potential new way to get that long-term continuous brain data, the EEG data, but less invasively than some current methods.
That's the idea. Less invasive than, say, intracranial electrodes placed directly in the brain.
Okay. And the umpire study is sort of the proving ground for this, the first real test.
A crucial first step, yeah, first in human trial, looking specifically at that initial safety and, does it actually work as intended, the performance.
Got it. So let's start right there. Based purely on your sources, what is this Minder system, technically speaking? And what was the umpire study's basic setup?
Okay, so the Minder system itself, your sources describe it as a bilateral subscalp EEG acquisition system.
Bilateral subscope. Okay, break that down.
Right. Subscalp means it's implanted just under the skin of the scalp, minimally invasive. And bilateral, that's the really key part here, records continuously from both sides of the head, left and right.
Okay. So not just one spot, but covering both hemispheres continuously over the long term.
Exactly. And the Umpire study was the vehicle to test that in people for the first time.
How many people? How long did it run?
It was what they call a prospective, multi-center trial. Involved 26 adults, and they completed a full 6-month follow-up period.
And the main goal was checking if it was safe, if it was feasible to use.
Primarily, yes. Safety and feasibility over those 6 months.
Okay, right. Now, this is where I think it starts to get really interesting. What did the study actually show about the system's strengths? What did it seem to do well in this initial run?
Well, first and foremost, safety. That's always paramount with any new implantable device.
And the results looked good on that front.
They did. Your sources emphasize a pretty robust safety profile over the 6 months. Specifically, they reported an absence of any serious adverse events related to the device itself or the implant procedure. No deaths either.
That's obviously huge. What about less serious issues? Any side effects?
The most common things were mild or moderate pain, like at the implant site.
Yeah.
That affected about 35% of the patients.
Okay.
But what's interesting is that your sources note these rates were actually lower than what's been reported for older unilateral subscalp systems.
Lower than previous tech. That's promising.
It is. And another really positive safety point. None of the devices had to be taken out or reimplanted during the study period.
Oh, that's significant too. Suggests it's pretty stable once it's in.
Right. It contrasts well with some earlier systems that apparently had higher reoperation rates. They also looked at lead stability, how much the implanted wires moved.
Do they move much?
Very little, actually. An average displacement of just 5.7 millimeters. And crucially, that small movement didn't seem to impair the quality of the signal they were getting.
So the space under the scalp seems like a good, stable spot for this kind of thing?
It suggests that, yes, the subgaleal space, technically.
Okay, so safety looks like a tick in the box for this initial study. What about actually doing its job capturing the brain's electrical activity? Signal capture, signal clarity.
Also quite positive, according to your materials. They did a direct comparison during periods when patients also had standard scalp video EEG monitoring, or VEM.
The kind usually done in hospital for a few days.
Exactly. And they found that basically all the key neurophysiological events they saw on the scalp VEM, things like sleep spindles, chewing artifacts, those between seizure spikes called IEDs.
Interictal epileptiform discharges.
Right. And actual electrographic seizures, the electrical signature of a seizure, all those were successfully picked up by the subscalp recordings too.
So it captured the same events. Was the signal quality comparable or even better?
This is another point your sources highlight. When they rated the clarity of the seizure signal subjectively, the subscalp EEG scored significantly higher than the 2-channel scalp recordings they used for comparison during VEM.
Significantly higher. Wow.
Yeah, the median score was the same, a 3, But statistically, the difference was significant. They quote a p-value of 0.0025, which is, highly unlikely to be chance.
Okay, and clarity for other signals.
Comparable. So for seizures, at least, it seemed to offer a clearer view in this comparison.
Now, let's circle back to that bilateral aspect you mentioned, recording from both sides. Your sources seem to call this a potential game changer. Why is that so important?
It really is a major advancement flagged in the papers. Think about it. If you're only monitoring one side of the head,
You could miss something happening on the other side.
completely miss it, especially if it's a seizure that starts and stays on one side, or if someone has independent seizure activity starting in both hemispheres. Bilateral coverage is designed to catch that.
Okay, so it gives a more complete picture. Did the study actually find instances where this made a clinical difference?
Yes, your sources state that this bilateral capability revealed clinically relevant information stuff they wouldn't have gotten from a unilateral recording in a notable number of patients. 6 out of the 26, which is about 23%.
Really a quarter of them. What kind of information?
Things like helping clarify which side seizures were really starting on when previous tests were unclear, or in some cases, detecting seizures starting independently on both sides when that wasn't suspected before. It really adds diagnostic value.
Right, it moves beyond just signal detection. How else did the study suggest this might be useful clinically for diagnosis or treatment planning?
Well, overall, they identified clinically relevant electrographic findings, those important brain patterns, in the vast majority of patients. 23 out of 26, so that's 88%.
That's a high hit rate for useful info.
It is. And it wasn't just one type of seizure. The system captured seizures originating from a diverse range of locations in the brain. So the potential isn't just counting seizures, it's about refining the diagnosis.
Like figuring out exactly where seizures start.
Potentially, yes.
Yeah.
Helping clarify tricky cases, maybe even helping assess if someone's suitable for epilepsy surgery by pinpointing seizure onset zones better than standard methods sometimes can.
Your sources mentioned a specific case, didn't they? Something about behavior.
Yes, that was a compelling example. In one patient, the system apparently identified seizures happening at the same time as episodes of aggressive behavior. This helped resolve uncertainty about whether the behavior was seizure-related or not.
So the continuous EEG provided objective evidence linking the two.
Exactly. It's the kind of clinical puzzle that patient reports alone, or even short VEM stays, might not solve.
Speaking of patient reports, let's talk about that issue of seizure diaries again. We know they can be inaccurate. Did this study add more evidence to that?
Oh, absolutely. The numbers provided in your sources are quite striking. During the time patients had simultaneous VEM, a full 56%, more than half of the electrographic seizures captured on EEG, were not reported by the patients in their diaries.
Wow. Half the seizures just missed in the diary.
Unreported, yes. And then look at the flip side. During those same VEM periods, patients reported 84 events in their diaries that turned out not to be seizures on the EEG,
84 non-seizure events reported.
compared to only 11 actual electrographic seizures that they did report correctly during that limited VEM window.
So lots of false alarms in the diaries and lots of missed seizures. Really highlights the discrepancy.
It really does.
Okay, so even though the Minder system wasn't recording perfectly 100% of the time for everyone over the 6 months you mentioned, average data availability was around 53%.
That's the figure they reported, yes. 53% mean availability.
Even with that, it's still capturing vastly more data than a typical 3 or 5 day VEM stay in the hospital, right?
That's the argument your sources make. Even intermittent use over months provides a much more extensive and arguably more ecologically valid, meaning representative of real-life picture of seizure patterns compared to diaries or short hospital stays.
More data, more context. And one last strength mentioned, it's subscalp, so it's considered minimally invasive.
Correct. Compared to putting electrodes deep inside the brain tissue, which carries different risks, that's a key advantage for this type of system.
Okay, so a lot of positives in this initial assessment. Safety, the signal quality, that crucial bilateral coverage, potential diagnostic utility, and providing way more objective data than diaries. But every study has limitations, especially a first-in-human one. What did this study not fully answer? What are the caveats here, according to your sources, that affect how we view the validity of its performance?
Right. Perspective is important. This was promising, but it's early days. The most obvious limitation, common in these trials, is the small sample size, just 26 patients.
Fine for initial safety, but hard to generalize.
Exactly. It limits how confident we can be that these results apply to everyone with epilepsy, given the condition's diversity.
Makes sense. What about more specific limitations related to assessing how accurate the device actually is at detecting seizures over the long term?
This is probably the biggest caveat your sources point out, and it relates to how the data was reviewed.
How so?
While the experts didn't review the entire 6 months of continuous subscalp EEG data for every patient looking for every potential seizure. Instead, they only reviewed the subscalp data during very specific time windows.
Which windows?
Times when a seizure was already marked on the simultaneous scalp VM,
Yep.
or times when the patient logged an event in their diary.
Ah, I see. So they weren't doing an independent, comprehensive review of the Minder data itself to find all the events it might have detected.
Precisely. And the crucial consequence of doing it that way, as your sources state, is that it precluded any systematic assessment of false positives.
Meaning they couldn't tell how often the Minder system might have flagged something as a seizure when it actually wasn't one.
Correct. We just don't have data on the false positive rate from this study design.
And presumably, it also meant they couldn't do a full analysis of all those unreported seizures outside the short VM periods either.
That's also true. They couldn't get a comprehensive picture of the true burden of unreported seizures over the full 6 months using this review method. Your sources are clear that these kinds of analyses assessing true positives, false positives, and the full unreported seizure burden based on a complete data review are planned for future studies.
Okay, so that's a major limitation for validating long-term detection accuracy. What else?
Another point was the relatively small number of actual seizures captured during that VEM comparison period. Only 25 seizures across 8 participants.
And that limited.
It limited their ability to really dig into certain things, like whether that small amount of lead migration they observed had any subtle impact on the seizure signal quality captured by Minder. Not enough data points for that detailed analysis.
Understood. And there was something about how the scalp EEG was analyzed for the comparison too.
Yes. The sources mentioned that the comparison scalp VEM data was initially screened using a commercial detection algorithm, not by a neurologist meticulously reviewing every second of it.
Okay, and the potential issue there.
The concern raised is that an algorithm might miss some subtle or very brief focal seizures on the scalp EEG that a human expert might catch. If that happened, it could potentially inflate the perceived advantage of the subscalp system's detection or clarity.
Makes a subscalp look better if the comparison standard wasn't perfect. Got it.
It's a potential confounding factor, they acknowledge.
You also mentioned the variability in data availability earlier, that 53% average, but ranging from 0 to almost 100%.
Right. That significant variability, 53% aneuploidy and 25%, range now as 97%, is noted as a limitation affecting data completeness and how representative it is.
Were there reasons given for the really low completeness in some cases?
Yes. Your sources mentioned 2 patients specifically where data acquisition was considered a failure. In one case, the patient had cognitive impairment that made it hard for them to consistently use the external part of the system.
And the other?
The other had a particularly thick scalp, which apparently prevented a reliable magnetic connection between the external device and the implanted lead.
Ah, so the technology itself has a physical limitation there. The magnet needs to connect through the skin.
Exactly. And they also speculate that because participants didn't get any feedback on their recordings during the study, they didn't know if they were capturing data correctly or not. That might have reduced motivation for consistent use.
Which could contribute to data gaps and make the results less reflective of ideal real-world usage.
Potentially, yes. It impacts that ecological validity.
One last point on limitations. Even with the Minder system providing objective data, the study still showed issues with what patients were reporting in their diaries, didn't it?
Yes, reinforcing the self-report challenge. Your sources note that around 69% of the events patients did log in their diaries during the VEM periods were not actually associated with any electrographic seizure activity on the subscalp recording.
So even when trying their best, there's still a lot of noise in patient diaries.
It just underscores how difficult subjective reporting is, even when you have simultaneous objective monitoring happening.
Okay, so pulling all this together now, the strengths, the limitations, what's the big picture takeaway from your sources on the Umpire study and this Minder system at this stage?
Well, the main conclusion seems to be that Umpire provides pretty strong initial evidence for the safety of the Minder system and also for its initial performance validity, meaning the technology itself, the bilateral capture, the signal clarity it works.
It seems like a significant step forward, especially that bilateral aspect.
It does. However, the validity of its comprehensive long-term seizure detection accuracy, how well it truly counts and characterizes seizures over months, that's still somewhat qualified.
Qualified by those limitations you mentioned. The way the data was reviewed, the completeness issues.
Exactly. This study wasn't designed or analyzed to give the final answer on its automated detection performance over the full 6 months.
Which means, essentially,
It means this was a vital and very promising first step, showing the device is safe and the core tech functions well. But further studies are definitely needed.
larger studies with different analysis methods.
Both, ideally. Larger trials, and critically, trials that involve a full systematic review of all the continuous data to properly assess both true positive and false positive detection rates over the long term. That's needed for full validation.
Right. So, safe tech works shows promise, especially bilaterally. But the final verdict on long-term standalone accuracy needs more research.
That sums it up nicely based on these sources.
Okay, well, we've definitely gone through the material you sent over. You asked us to do a deep dive into these notes and papers on Ampere and Minder, and hopefully we've pulled out those key insights for you.
The safety data, the potential of that bilateral monitoring, the stark reminder about self-report limits.
And those important caveats about what this specific study can and can't tell us about long-term accuracy just yet.
It really does feel like it could represent a potential shift, though, towards monitoring that's less invasive, much longer term, and maybe more complete than what's often possible now.
And thinking about that potential shift, maybe here's a final thought for you, the listener, building on these sources. If this kind of continuous bilateral brain activity data becomes more common, more accessible outside of just short hospital stays,
Mhm.
how might that change things fundamentally?
Mm.
Not just for diagnosis or picking treatments, but how might it change how people with epilepsy actually understand their own condition? Seeing the objective data, perhaps beyond just the seizures they feel or count?
That's a powerful question. What else might we learn? What patterns might emerge? When we can essentially watch brain activity unfold, uninterrupted, for months or even years, it opens up a lot of possibilities.